Hello, dear colleagues. I'm grateful for the opportunity to present our work on a new combined kernel projection statistical estimator and its application to the radiation intensity evaluation. This is joint work with Professor Gennady Mikhailov and Professor Sergey Ukhinov, and my name is Natalya Tracheva. So I'll start with our motivation. And our motivation is the problem of evaluation of some kind of probability density. So in one-dimensional case, there exist a number of methods to do this. So the most common way to evaluate one-dimensional probability density is the kernel density estimator. The theory is described in Borovkov and Iponechnikov and lots of other works. There are lots of works on how to choose the proper averaging window. And another approach was proposed in our work of 2016. And in this work, we proposed the randomized projection estimator. The idea is to expand our function in terms of some kind of basic orthogonal functions. So we have expansion, series expansion, and we can evaluate coefficients with Monte Carlo method. And the basic questions here, how to choose the proper set of basic function and how to choose the proper number of coefficients in consideration. So where to stop evaluating next coefficient and it's a huge problem that for one set of basic function you can get very quick convergence, and for another basic function set you'll get a very poor convergence in terms of number of series terms. But still, what about the multiple case, multidimensional case, for example, two-dimensional case? What are the choices here? Once again, two-dimensional kernel density estimator. But for the kernel density estimator, the Karasov dimensionality is working, and in this case, the convergence rate is worse than in one-dimensional case, so it's not very efficient. Depending on how you implicate the method, you can need a lot of memory to implement it, and you need some kind of preliminary pre-processing of the information of the data. So it gives us the great increase in the computational complexity. And in our work, we suggested the two-dimensional projection statistical estimator, and everything that holds for one-dimensional case holds for two-dimensional case, though we have got good agreement with test results. So numerically, we obtained that two-dimensional projection statistical estimator is working, but theoretically, we have no information on how to choose the proper set of the orthogonal function, and that is essential for the method computational performance. So thus we have the idea of the kernel projection statistical estimator. It's some kind of combination of projection and kernel approaches. So here we expand the function in a following way. So we have two-dimensional function, density function, and coefficients depend from one variable, and density. Orthogonal basic function depends on the other. So this is Kronecker symbol. So basically here we can get the coefficients in the following form, and we can get the statistical estimator of the following form. So here is the kernel density, kernel estimator for the coefficient a sub I, and here is the orthogonal basic function psi sub I. And in this case, we have three parameters to optimize to get the optimal estimator. This is the parameter m, number of terms of the expansion, like in one-dimensional case, and like in two-dimensional case when we have the just projection statistical estimator. And here we have number of realization, and the parameter of delta is the averaging window for the kernel estimator. So there are three parameters, and we are interested in finding the optimal values of that. So optimization of the kernel projection estimator. We consider the mean square error, so we can rewrite it in the following form, and we are going to consider these terms here separately, and I'm gonna to give you a sketch of reasoning for the optimal values that we've got. First of all, we consider the first term. We can rewrite it in the following form, and for the so-called tail of the series expansion, we imply the following inequality, asymptotical inequality. So we have some kind of function and some kind of constants to evaluate the asymptotical characteristics of the these series. So we using the orthogonality of the set of psi sub I, we obtain the following inequality, and applying additional restriction, we can get the following inequality. So we have some kind of constants we should evaluate to get the optimal values. And note here that there is the second derivative from f1, the which depends only from x. That is integral of the function f from x and y. And so this is quite a trick to evaluate this constant f sub 1 here. So I'll discuss it later. And for the second term, we can expand it in the following way, and then using orthogonality once again can get the following, keeping in mind that delta is essentially lesser than 1. So once again, implying some restriction, additional restriction on our function f from x and y divided by integral from this function, we can get once again evaluation of the second term here. So as for the optimal value of delta, okay, so now we have the following asymptotical equality. This is mean square error, and we have constant f sub 0, f sub 1, and f sub 2, which we can evaluate. And minimizing this value, we can get the optimal delta here. And we can evaluate the mean square error here and the rate of convergence. And note here that the rate of convergence is the same as for the one-dimensional kernel density estimator. So it's not like the two-dimensional kernel density estimator. What about the SM? So for the tail convergence rate, we consider the following. From the work of Chintsov, it's known that convergence rate, when convergence rate of have the following form, and we can find the same in the work of Smilov. It was shown that for the expansion of airtime continuously differentiable function over trigonometrical polynomials, such convergence rate holds. So we suggest that the square of this value equals to the following, and once again minimizing our mean square error approximation, asymptotical approximation, we can obtain the optimal value of m here. But practically, we implement the optimization under assumption that our coefficients decrease exponentially. So this assumption calls for the problem we are considering here, the problem of an angular distribution of the particles that were multiple scattered in the medium. We know it from our previous works, for example, from this work. And within this assumption, we can get other values of m and delta, and once again we can evaluate the mean square error for these values. It is the optimal, the minimum value here. So how can we verificate this method? We consider the problem of estimation of an angular distribution of radiation. So we have some kind of layered medium. For example, we have layer from 0 to h. This is the optical thickness, and we have some incident radiation, and it passes through the layer and escapes from it. So we can have transferred forward radiation and backscattered radiation. So we are evaluating the angular distribution of the transferred and backscattered radiation. Forward scattered and backscattered radiation by this layer from 0 to h. Mathematically, we consider the stationary integral differential radiative transfer equation of the following form. All theory can be found in the work of Marchuk, Mikhailov, Nazarliyev, and others. The Monte Carlo methods in atmospheric optics. And here we have the phi is for radiation intensity function in point r and direction omega. Omega is from the space of unit direction vectors, r from the three-dimensional space. So G is the radiation indicatrix or phase function. Sigma is the total cross-section. It is the characteristics of the medium, and the it's equal to the sum of the absorption cross-section and scattering cross-section. And of course, we have initial distribution density, so some kind of source here. And we consider the transfer of radiation as a Markov chain of collisions photons with the particles of matter. So we use the trigonometric expansion here to estimate the density of distribution of radiation flux that passed through this surface that equal h. We consider this basic expansion, so it looks like following. Here, mu is the cosine of the zenith angle, phi is the azimuth angle, and mu varies within the interval from 0 to 1. And obviously, you can find the coefficients here in the following way. But here we constructing our system in a way that distribution density that we are looking for is symmetrical regarding the initial plane of incident radiation. So coefficients with sinus is eliminated and equal. So we have b sub I equal to 0. And for some kind of arbitrary point mu sub k in the interval 0 to 1, coefficients of expansion are evaluated with the use of kernel averaging of the optimal interval delta, and it was obtained from preliminary estimation. So I'll discuss it's a little bit later. So Monte Carlo estimator has the following form here, and we construct the Markov chain of collisions xk and it is the pair z sub k, that is z coordinate of the collision point, and omega sub k, that is the direction of particle before the scattering event. And when we scatter forward, the delta sub s equals to the following. When backward to the following node, here we have the upper boundary h, and here the bottom boundary 0. So we have the layer 0 to h. Thus, the delta sub s is the indicator of intersection of the boundary. So delta sub j from mu k is the indicator of the mu k hitting the jth interval, mu j minus mu j. That is comes from the partitions on delta sub mu. So we hit the interval of delta. So we have the weight q, that is q capital divided by delta, and q capital is the scalar weight that determines by the modification of Monte Carlo method of simulation, free run and absorption, and so that is some kind of technical simulation weight. All this information about Monte Carlo estimator on escape without absorption, without escape in simulation, you can find once again in the work, the Monte Carlo methods in atmospheric optics. And mean square error for this estimator, on each interval, we can evaluate in the following way. So how can we verify these methods, the results from the computation? To verify it, we construct approximation from the local Monte Carlo estimator. So once again, from you can find the information about local Monte Carlo estimator in the work of Martyuk, Mikhailov, Nazarlev. We predefine some set of direction in which our radiation escapes from the plane, and we construct the local estimators in each point of this predefined set. We construct such kind of estimator, and based on these estimators, so we obtain the result in these particular points, and using linear interpolation, we obtained the approximation of intensity of transferred radiation to compare with. So we have some kind of benchmark results. And here's a slide about evaluation of second derivative for finding the f sub 1 to obtain that parameters, we preliminary construct the microgroup sample. How do we do this? So it's kind of trick. During the Monte Carlo simulation, we obtain the microgroup sample, and from this microgroup sample, we reconstruct the small f sub 1 function using the orthogonal series expansion. So it's just one-dimensional projective series expansion. And we used in our problem two kinds of polynomials, orthogonal basic function, modified Legendre polynomials, and modified Jacobi polynomials. And so we have f sub 1 in a following way. We can find coefficients as integrals of such form, and integration is evaluated with summation from the micro intervals of the microgroup sample. Thus, we can get the second derivative, and moreover, we can get the squared second derivative integral. Note here that both set of polynomials gave quite similar results. So, and in the case of some kind of peaky shaped indicatrix, you can divide the interval 0 to 1 to sub-intervals, and on each such kind of intervals you can evaluate in a similar way, but you should consider different normalization here for the polynomials according to the intervals you are considering. And to the numerical results. Simulated medium. Which kind of mediums we have considered? So we have the molecular scattering in the medium that is simulated with well-known relay indicatrix, and for aerosol scattering we use such parameters to evaluate the indicatrix with help of Mie theory, or the theory you can find in Dirmidjan, for example, and it is basically the water drops that distributed logarithmically with such kind of distributed with logarithmically normal density, this form. So that is aerosol scattering and molecular scattering we are considering. So to numerical results. First of all, I show you verification of the numerical results, and on this slide I show you angular distribution function of normalized flux of radiation transmitted by a layer, so it's on an upper boundary for molecular scattering. I'll just show the pictures here on the A. So you can see that the cross line here is the local density or local estimator, and the squared line here is 3 sigma confidence interval for the local estimator here. Long dashed is for the phi sub 1. It's the first, it is the approximation with the first cosine coefficient, so 0, and first cosine coefficients here. It's you can see it's not good enough, but for the second coefficient, that is the solid line here, we can see it has great agreement with the local estimator. And the third one, as the third coefficient has a higher statistical error here, it gives some statistical error, and it's still within the 3 sigma confidence interval for the local estimator, but it's not very good right now. So it is for the incident angle of 45 degrees, and we are the observation angle is 60 degrees, and the optical optical thickness is equal to 4, h equal to 4. So for this picture, it shows the same characteristics, but it's once again for the optical thickness of h equals to 1, and the incident angle theta sub-0 equals to 30 degrees, and the observation angle is 45 degrees. So once again, you can see the local estimator, the 3 sigma confidence interval with squares, marked with squares here, and the optimal, once again, equals to 2. So m equals to 2, and you see it's optimal. Adding other coefficients, third one does not improve the approximation, and it's not necessary. So on the next slide, I'll show the dependence from the delta interval here. Delta is the average window of the kernel estimator. So this is pictures here. Once again, the first one is for h equals to 4. Theta sub-0 initial incident radiation angle equals to 45, and observation angle equals to 60. So here we have, once again, local estimator is a cross line, 3 sigma confidence interval is the squares line, 2 lines here. Solid line is for the theoretically optimal delta. It lies quite within the 3 sigma confidence interval. Long dashed line is for not optimal delta, that is essentially larger than optimal delta, and short dashed line is for delta that is less than optimal. Note here that they are not so far away from the local estimators, and each of them has its own 3 sigma confidence interval, so it's not that bad. But still, keeping in mind the small range here, I think it shows that the optimal interval still gets the better approximation. And on the right side, you can see for h equals to 1, the optical thickness of the layer. Initial incidence radiation angle is 30 degrees, and observational angle is 45 degrees. So once again, for the optimal delta, you can see good agreement here. And for the delta that are not optimal, that is lesser and larger than optimal values, you can see it is not very good approximated at this initial area. So it's part of the this. So it's this part of the such kind of pictures. So, and thus we conducted computations for different optical thicknesses through optically small to optical thick layers, and for different initial radiation angles, and for different observation angles. And we have some profiles of these values, so the function, density function, and we investigated the optimal values, theoretical and computational. So these are the theoretical optimal values here. So I just spent a little time on this here, for different optical thickness. And once again, it is molecular scattering, backscattered, forward scattering. And I should note that for thin optical layers, for some angles, you should have quite many coefficients to evaluate the angular density. Good. So this is another slide. And once again, it is for thickness of H equals 4, transferred radiation and backscattered radiation. And to the conclusions. So we propose a new combined kernel projection statistical estimator of the two-dimensional distribution density, where the first main variable is processed with the kernel estimator and the second one is processed with the projection estimator for the conditional distribution density. The mean square optimization of such an estimator is performed under some assumption made about the convergence rate or the orthogonal decomposition in the use. A number of studies, a numerical study of the constructed estimator is implemented for angular distributions of the radiation flux forward scattered and backscattered by a layer of matter. And a comparative analysis of the results is performed for molecular and aerosol scattering. And for this type of problems, we have some recommendation. One should simulate at least 3 expansion coefficients with averaging over mu interval of approximate length of 0.06. And in the case of forward extended indicatrix, the number of terms of the expansion series should be increased up to 10. So basically you need, in vast majority of cases, you need just 3 coefficients, and the approximate length of the optimal delta averaging window is 0.06. So this is all. Thank you for your attention. Good luck.